By the way, I want to remind everybody that this class is graded on a 12-point scale. Right, so 88 is an A and so on, right? 88 and higher. So there was a very wide range of scores on here. Some did extremely well, some did very poorly, and I'll say some things about that as soon as I get these turned back. So James Tucker. Scott, I don't see Scott. Estonia. Daniel. Okay. And Alex. Eric, I don't see Eric yet. Tina. And Michael Shooks. Sorry, Michael, I'll get that name soon enough. And Chris Loa. Go. Okay. And Roman's not here. Don't see Melissa. And Austin. Don't see Austin. And Zach. Okay. And Joseph. Right. Okay. Okay. Trevor. I don't see Trevor. Chris McGraw. Okay. And Philip. I don't see Philip yet. Sarah. Okay. And Jonathan Anderson. And Scott. Okay, so I've got a few more of these left. So hopefully all of you saw the solution. If you want to discuss your test with me, by all means, bring it by. We can talk about it if you're concerned about what happened. If you did well, and there were several people who did extremely well on this test, then that's great. Keep it up. If you did not so well, there are two things that I need to say about that. First of all, something needs to change. Okay, and some of you are working your way up, and I have seen students do extremely poorly on the first test and recover and try to get it by the end, and it does happen. Okay, but it only happens when the student clearly starts putting in or continues putting in a lot of effort, coming to office hours, and making sure these things are ready, right? That you're ready for the exam, that you've covered that you understand all the problems that are there that have been done already. And also, I do look favorably on, progress, right? So, if you show steady increase and, come out really well in the final, then I won't pay as much attention to the first test, okay? Like I said, it does happen that students do, quite poorly actually in the first test and then recover and really get it. But you've got to change something, right? Or, continue just working at it until it, until it goes. And sometimes it's just like, people say something clicks. It's literally like a click, right? That all of a sudden, you understand what you have to do. And that's not something that's just handed down magically from the air, right? That comes from doing, working on this stuff a lot, right? So that should be your strategy if you're not happy with how your first test came out. Okay, so talk to me if you have questions about it. Today we're going to do basically the first really substantial proof that we've done in here. We're going to prove that square roots exist. Okay, but before I do that, I want to do one quick example of how to calculate a sup of a very definite set. And you'll have various exercises along these lines. First of all, so I think all of you are familiar with intervals. We've even used them. So definition of intervals, right? They're closed and bounded intervals, half open intervals, open intervals. I'll write down the definition of one here. The rest are very similar and they're all listed in the text. I don't think you guys will have trouble with that particular definition. So for example, if we look at A comma B, that's a set of all x and element of R. such that A is less than X less than or equal to B. And of course, in this case, we want to have A less than B, otherwise it's not going to make any sense with those inequalities. Okay, so let's consider a concrete example. Let's let A be equal to the interval from 0 to 1. Okay, so let's talk about, so the definition of this, right? I mean, we can just take that. So this is, I'll just write it down, this is the set of all x, an element of R, such that 0 less than or equal to x less than 1, right? So one thing we can say immediately about this by one of your homework exercises, in terms of sups and infs, maxes and mins. What's one thing you can say immediately? And you've hopefully by now worked on this exercise, and it's not an easy one. Yes?
One is the sup.
Well, we don't know how to do that yet. That's going to take some work. But what about the other end?
0 is a minimum.
Why is 0 a minimum, guaranteed?
It's in the set.
And?
A is the lowest element in the set.
Well, you don't even need to know that, right? It's not really the lowest element in the set. It's more generally, what is it? It's a lower bound, right? There it is right there. This is all x that are bounded, right? That are greater than or equal to 0. And then there's another condition, but that doesn't matter in terms of lower bound, right? But if you have something that is a lower bound for the set, and it's in the set, so that's the equals part there, then by this exercise that again, you should have worked on by now, right? And if you didn't, then this, and you're not doing well, that could be part of the issue, right? Tells you immediately, no more work, right? That 0 is the minimum. This is by a previous exercise. Now we're going to have to work a little harder for 1. And I'd like you to think for a second about using the original definition, the S1 and S2, right? So certainly 1 is an upper bound, right? But in this case, it's not in the set, so you don't have that easy way out. And so if you're going to use the definition, you'd have to pick up some kind of another upper bound for the set, and you'd have to show that that's bigger than or equal to 1. Well, if you use the definition, then all you know is that all the things in here are less than or equal to that thing, and you're still going to have to do some kind of work, right, to show that that upper bound is somehow bigger than or equal to 1. Okay, so I won't go into details about why it's not immediate. Okay, I'll let you think about that, right, and go ahead and try to prove it that way. But it's going to be more straightforward now to use the approximation property. So we're going to use approximation property to show that 1 equals the sup of A. All right, so what was A1? We had these two conditions, A1 and A2. What was A1? Otherwise known as
S1.
S1, which means,
There is an upper bound.
yeah, so 1 is an upper bound by definition, right? Because the definition tells you that everything in here is actually less than 1, not even less than or equal to 1. Okay? Let's look at A2. Okay, who can tell me what A2 says? Yes?
For every epsilon greater than 0, there exists some little a in big A such that A is greater than S minus epsilon.
Okay, right. And so, but instead of S now, what are we going to get? Yeah, A is greater than 1 minus epsilon. Okay? So let's draw a picture here. So here's 0, here's 1. And now what you want to do, of course, you always think of epsilon, everybody does, right, as being something small, right? And usually that's the idea when you're dealing with epsilon. You want to think of it as being, arbitrarily small, right? So you draw it like this. But there's a little bit of an issue here because you don't know how small epsilon is, and it is for every epsilon, not just for small epsilons. In fact, I don't even know what I would mean by small in this situation. So it's possible that the epsilon that somebody hands you, and remember, you got to take every epsilon that somebody hands you and work this out. It's possible that your 1 minus epsilon might be way over here. Oh, there I made a German one, right? Some of you are struggling with that in one of the other classes I heard, right? Okay, so right. Okay, so then if you pick your A, you're still bigger than 1 minus epsilon, but what's the problem?
You're outside.
You're not in big A, which goes from here to here. So that's the only tricky part here. We have to be careful to make sure we don't overshoot our set. Okay? So how are we going to do that? Well, our element in here, we're just going to call it 1 minus delta. And what we can do, of course, we have a lemma that tells us that we can choose delta how?
Delta is greater than epsilon is greater than 0?
Less than epsilon. 0 less than epsilon less than, sorry, 0 less than delta less than epsilon, right? We can choose it smaller, okay, right? Okay, which would put us in there, but again, we don't want to overshoot it because that 1 minus delta could be over here. So what we're going to do is we're going to make sure that our delta is smaller than what? What would force it in there? In fact, what would force it to be to the right of a half, which would guarantee us that we're in there? For 1 minus delta, right? If we choose delta also smaller than a half, then 1 minus delta is going to be to the right. Okay? So we're going to let, so by a previous lemma, we can choose, exercise or something, choose delta bigger than 0 such that delta is less than the minimum of 1/2 and epsilon. Right? Because this is a positive number. Because epsilon is positive and a half is positive. We get to use all the stuff you learned in algebra, so you know a half is positive these days, right? Okay? So the minimum is positive. So then I can choose some positive delta that's actually smaller than that. So then I'm going to let A be equal to 1 minus delta. Now we need to check that A is actually in the set big A. That just means checking inequalities. So let's see if we use these two facts. So if we use delta less than a half, what does that get us? That means that A equal 1 minus delta is bigger than 1/2. Okay, so what do we know about this thing? And we also know that 1 minus delta, what's the relationship between 1 minus delta and 1? See, now we're just doing math, right? Like you used to remember, okay? So now you got to be good with inequalities. Sorry, is less than 1, why? Delta is bigger than 0. Right? We're subtracting a positive quantity. And for a while, we're just going to be doing math as you used to know it, right? But you have to be so careful, and you have to think carefully about it, right? Okay, so this is what analysis is about. Okay, so if we put these two together, we have what? We have 1/2 less than A less than 1. So this is A equal 1 minus delta, right? And so what does that tell us? Where is little a? But where are we interested in A being, little a? Where do we want it to be?
In the set A.
In the set A, and it is, right? Because to be in the set A, you just have to be between 0 and 1, and we're actually doing better than that. We're between 1/2 and 1. So it's in there. You guys need to get really, really good at doing inequalities, and I'll make sure that happens in the next few days, okay? And that, I don't care what you do. If you decide you don't want to do math because of the proofs and you go to engineering, you got to be good at inequalities, right? Because inequalities are how you estimate your error. And as I always tell my calculus students, most of whom are engineers, that when you do your work, you will always be wrong. And the goal is to not be so wrong that your bridge collapses or something, right? So understanding your error is extremely important, and understanding your error is exactly about inequalities. Yes?
Can you explain the second to last line again, please?
This one here?
Yes.
Okay, so we have here that delta is bigger than 0, right? So what does that tell? I mean, if we want to really break it down, right? What does that tell us about minus delta? Less than 0.